just a terrace and a bed. It also now has a substrate, and the size distribution within that substrate may include both sand, bed material, which in this case would be sand, or mud. So we have mud and bed material now. Same thing for the floodplain. The floodplain could have mud, some fraction of mud, some fraction of bed material. But the active layer of the channel, just for simplicity, we assume only includes bed material. Okay, but just one size for now. And we'll again develop this series of connected boxes. Okay, so this is what it looks like. I'm not drawing the boxes on both sides of the channel right now, just on one side, but it's still supposed to represent a system that has a floodplain on either side of the channel. But here's our floodplain storage box. That's sort of analogous to the terrace in that last model. And then we have our substrate in our channel. And now we can have, rather than the flux through the bar and then the flux back from the floodplain into the channel, both of which are calculated given a specified migration rate C, there's also an overbank deposition term. That's how you stack the fines onto the floodplain in the first place. And that could raise the average elevation of the floodplain and change the size distribution for the floodplain. It requires an overbank deposition model, pretty simple model here. It's really essentially a trap efficiency model. So if you can calculate the total flow of sediment across the floodplain, suspended sediment concentration C times water discharge across the floodplain from the flow partition F, multiplied by a trap efficiency factor, FL in this case, you can get a flux, and this is the flux per unit down channel length. So you have this scaling factor, the channel width in there. Let's see, I've already talked about how you calculate the overall erosion-related exchange or bar deposition fluxes. There's also, now if you're grading or degrading, we'll have to move sediment into the substrate or take it out of the substrate. So there's this flux associated with the movement of the boundary. And then it turns out that it's important to characterize the size distribution of the material that's moving through the bar into the floodplain deposit. So the bar we usually think of as being entirely bed material. But here, if we're trying to represent a real system, there are other ways that you can exchange material with a floodplain. And certainly, you can get material into low parts of the floodplain, find material into low parts of the floodplain. You can have drapes of mud on the bars. You can have chutes that scour and then fill with fines and so on. So we wanted a factor that allowed mud to accumulate in the bar as well. So this is that factor. If K approaches, let's see, infinity, it would be all mud. And if it approaches 0, it would be all bar material. Okay? All right, and so again, we just connect these boxes in series, but now we have slightly more complex exchange, not just back and forth between the terrace and the channel, but now there's this exchange or transfer into or out of the substrate as well. Okay? And it turns out that there's an equilibrium possible in this case, not necessarily required, but it is possible that if you let it run for long enough, you'll approach an equilibrium elevation for the floodplain, just like before, and you'll also approach an equilibrium size distribution in the floodplain and in the channel. Okay, so this is now a case where we're simulating the Minnesota River evolving in this model. This is sediment supply, and this is just mud. We're only supplying it now, not with bed material load, but with wash load. When you see, I'll hit here a bump where we double the load, and watch what happens to the floodplain. Okay, the red line is the floodplain, the blue line is the bed. I'll let it go through a couple more times so you can take a look at it. And you'll probably find that this is very counterintuitive, and I'll let you think about it for a minute.
Yeah, why does the floodplain go down?
Yeah, why does it go down? Well, it actually goes up first.
Yeah, of course, but
so it's stable right now, and then we're going to hit the extra supply. And when it's hit, the floodplain actually goes up, right? Sedimentation occurs on the floodplain when you're overloaded with sediment. That's intuitive. But the thing that was not intuitive to me the first time I did this run was that the bed would go up too. I would not have expected that. In fact, I expected that a higher floodplain would mean you would have more flow in the channel, higher shear stresses, more down-channel transport capacity, and the bed should have been sized within the channel. But it didn't, right? It's actually cut off. And then when you're done, once the pulses move through, then that happens. Then it finally starts in sizing. So I'll let it happen one more time, and then I'll tell you what I think the answer is. Up and back down. All right, so this is what I think is happening. You're bringing material out of the floodplain. We overloaded the system with mud, which meant, based on our partition model, that we had to put mud in the bar, which means we couldn't put all of the sand back in the bar. Okay, so we started from a case of equilibrium where the amount of sand eroding from the bars, well, from the lower parts of the cut banks was being replaced in nearby bars. Once the system gets overloaded with sediment, because of our model, which may totally not be right, but because of the way we specified this sorting, if you want to call it that, this fractionation between sand and gravel in the bars, we made the bars finer. We put a lot of mud in the system and the bars became muddier. And because the bars became muddier and we didn't let the channel widen, we didn't let it adjust any other way, the only place that that extra sediment could end up was on the bed, and that's what caused the aggravation during that time. Okay? So, key points. This may not be right, but it is possible for the bed to respond to an increase in mud. Well, in this model, the bed increases because it displaces sand from the floodplain. And if you wanted to do morphodynamics in a system that has a lot of sediment exchange, I think that means you really need to pay attention to the size distribution of material that gets deposited in the floodplain. So that's the first point. Second point is, we did focus flow on we focus flow into the channel by filling in the top of banks and the channel in size as a result. Okay? And this just illustrates essentially the same thing. I think I'm going to skip this for sake of time right now. But basically, I'll go through very quickly. Floodplain elevation stays low until you overload it with mud. It goes up, and then it reaches its equilibrium again. The floodplain sand fraction goes down by a lot. Again, our partitioning may not have been right here, but in this model, we moved a lot of mud into the floodplain when we overloaded the system with mud. Okay? But eventually, it approaches an equilibrium. The real Minnesota River is quite a bit more complicated. So I'm going to spend a few minutes here talking about a sediment budget that we've been trying to develop for the Minnesota River that accounts for lateral exchange processes. So this is a photograph of the Minnesota River in 1940, I can't read that well, but I think it's 46, 2008. There's a lot more flow in the river now than there used to be. In fact, this is one of the longest gauge records in the United States. And this is at 1% exceedance daily discharge for each year in the record. Actually, there were two different data sets. One of them was from annual data, which didn't go back as far. The other one was just some spring through fall flow. They didn't measure flow in the winter early in the record. But in both cases, that 1% exceedance flow has increased pretty dramatically over the last century. It's probably a result of agricultural development of the basin, putting in drainage ditches that connect prairie potholes and swamps to the channel now. So there's less of evapotranspiration that occurs in those areas of the uplands than there used to be. So flow, it could be climate too. And then here's the flow duration distributions computed for the first and second half of the record. And if you compare the ratio of those two flow duration curves at any exceedance probability, the increase has been a factor of 2 or 3. So first half of the record to the second half of the record, the flow essentially doubled at just about any part of the hydrograph. Maybe tripled in some cases. So that led to the rivers widening. They adjust geomorphically. And we've tried to make measurements of the widening rates on these rivers using air photos. Basically every historic air photograph that we could find within the watershed. This is the watershed here. We split it up into the large main stem, actually the part that's named the Minnesota River, and then the major tributaries, they also tend to have names, and then a lot of the smaller first, second order ditches and channels. And then we sorted our widening rates that we had measured from aerial photographs into those bins. We see larger rates of widening on the main stem and the larger channels than we do on the small trips. That doesn't mean that they're not widening, it's just that we don't see it. They're small, so it's really hard to measure migration on really small channels. So they may actually be migrating and they may be widening and we may not know it, or maybe they're really not. But for now, I'm just going to use what the data tells us. It looks like we have the highest widening rates here on the blue part of the system. Okay, so how much, was that real change? Is it just widening and getting shallower? Is that sediment just sort of coming in and filling up the cross-section? Or is the channel actually changing throughout the whole section? We actually looked at the water surface width whenever we had an air photograph and wanted to see whether the attestation hydraulic geometry, you can get a relationship between water surface width and discharge for any of those historic air photos, because we know what the discharge was on the day of the photograph. And we plotted those for the first half blue and the second half red of the record, and it looks like you have a different hydraulic geometry for water surface width in the second half of the record than in the first. So I think these cross-sections really are enlarging. Okay? Well, how much volume are we talking about? So we actually looked at cross-sectional geometry throughout the whole Minnesota River Basin at all scales, from those small channels all the way up to the main stem Minnesota River, fit a power function through that. And from that we were able to get an idea of where all of the bankful volume was in the basin. And it turns out that most of the volume is probably in the blue part, the Minnesota River. So this is the small first and second order tributaries. These are the named tributaries, and this is the main stem Minnesota River. Okay? So it turns out from the hydraulic geometry, you have most of the volume in the system in the big lower main stem part. And the widening rates seem to be the highest there as well. So that can account for a lot of sediment. The main stem Minnesota River, I'll go back one slide, this part right here starts, it accounts for this much, maybe 20% of the overall bankful volume in the basin. So we tried to put it, just last night I was putting together a budget just for that part of the system. There's a gauge sand and mud transport rate from suspended sediment concentrations at the upstream end of that system. The gauge load, gross 1.6 million tons per year, and sand was 26% of that, so about 450,000 tons per year. How much sediment exchange did we have? Well, just from the widening, and let's forget about migration right now. So we know how much widening we were getting, that's production. Gross, we were getting 620,000 tons, or maybe 285,000 if you take a look at some size distributions that we have for floodplain material, which are roughly 50-50 sand and mud. And we actually do have migration rates too. It's widening while the channel is shifting, and I'm not going to go into it, but you can back out how much of that is shifting and how much of it is widening. When you do that, it looks like the shifting accounts for another 450, 500,000 tons per year gross, or maybe, again, 200,000 tons sand. So what you end up with is sand coming in, we're depositing a little bit, we're showing a little bit more sand deposited from migration than eroded, and that's because the bars are not 50-50 sand. In this case, the bars are more like 90% sand and maybe 10% mud. Okay? So we're probably eroding a lot of sand from the widening and from the lateral migration, but because we're creating bars that are quite a bit sandier than that deposit, we're not necessarily exporting that material downstream. We are exporting, well, we're producing a lot of mud, but independently there are some other budgets that have been done for mud. Previously they had come up with a storage of about 300,000 tons per year within the reach. We need to add probably another 500,000 to that number because of the net supply of mud that we've got because of the widening and the channel migration that's going on here. So the point is these are complexes. They're complex. There are many ways that you can get sediment from a floodplain into a river, and it's not just widening or migration. There you can come up with a bunch of processes, avulsion, floodplain stripping. There are a lot of ways you can do that. But the size distribution of that material would be important, and the size distribution of what gets left behind as the channel moves away somewhere else would also be important. Okay, so I'll finish the talk by talking about the Elbow River, which is in Washington State. It's an interesting place because there's a dam. There were two dams constructed starting about 100 years ago. They blocked all fish passage into what is now Olympic National Park illegally, and when they came back for certification 20 or probably 30 years ago now, they decided to remove the dams to provide fish passage into Olympic National Park. So two dams, lower, let's see, there's Lake Aldwell, lower, the Elbow Dam here, and Blind Canyon. Both of them are out now. Blind Canyon Dam was taken down in a series of steps, and the last step was removed about a year ago, so last summer. Okay? They're really big. So 64 meters for Blind Canyon Dam. Elbow Dam was 34 meters, so this is the largest and the third largest dam ever removed. And they've been accumulating sediment for 100 years. So we have 100 years worth of sediment that's now been released into the middle and lower Elwha rivers. The middle Elwha is between the two. The lower Elwha is below the lower of the two dams. You can see deltas that had formed. The nice thing about this is because these deltas had formed, we have a good idea what the overall sediment transport capacity of the system was. And in addition, we have an idea what the size distribution was for that material. So back when they were planning these projects, the U.S. Bureau of Reclamation drew down the reservoir and did a bunch of sieving and coring of the delta deposit. And they came up with a deposit that was roughly 50% silt and clay, 37% sand, 30% gravel, 2% cobble. you could do a transport calculation, but I tend to like absurd numbers. So we have some idea what the long-term size distribution might be for the system. I don't have a lot of confidence in this particular number here, but it's something. Okay? So we can do these exchange distance calculations here as well, just using that first sort of naive way of doing it that I started with, where we just compare the load to the size-specific transport. And lateral exchange. So lateral exchange over the time since the dams have been in place, 1.3 meters per year migration. That's probably a little lower than it was before the dams, but in any case, we have some idea what that number is. Bulk density, let's see, I made some wild assumptions here about what the bank height would be. I looked at a photograph to come up with the size distribution for the material being eroded from banks. And let's just assume that that is similar to the material being deposited. So we can come up with our size-specific exchange rate, our size-specific down-channel transport rate. When you do that, you get exchange distances that are strongly dependent on sediment size, just like we started with. So the fines has a very long exchange distance, but the cobbles, again, 5 kilometers or so. So even one of these small reaches between the two dams is longer than that. Okay? And this is what it looks like downstream of the dams before the dams were removed. This is a bar on below the lower of the two dams, almost entirely cobbled. And if you walk up, this floodplain has been reworked in the time that the dams have been present. This bar has very few fines. Well, it has a lot of fines in it now, but before the dams have been removed, virtually no fines. There's sand, but very little mud at all in that bar deposit. Okay? So now a more complex model still. Where we'll still have overbank deposition, we'll still have lateral exchange into a floodplain deposit. That previous bar sort of represents that deposit here. But now I want to keep track of size-specific fluxes within the channel zone. So using a size-specific transport, gravel transport equation, we use Wilcox and Crow or equations similar to that. And we'll still have to come up with a size distribution for material being moved into the floodplain. So here we'll use Hoey and Ferguson transfer function. So it's a mixture of the load that we calculate within the from the distribution of the surface of the active layer and then the surface of the active layer. I said that in a weird way. It's a mixture of the load and the active layer that goes into the bar. And then if the system abrades because of this pulse of sediment released by the dam and then comes right back down, we want it to work that material that it just left behind. So we split the channel and the substrate zone, the substrate into a channel and floodplain zone so that can happen and it doesn't unreasonably mix the sediment across too large an area. Okay? But in other words, it's basically like that initial toy model. We have these zones where we have exchange going on back and forth between all these reservoirs. Okay? We can actually calculate an equilibrium for this system as well. If we know what the fluxes into the floodplain should be, and we know the size distribution that the system would have in equilibrium, we could actually even calculate what the size distribution would be for our box. And if we have an overbank, long-term average overbank deposition rate and an average reworking rate, we could get an average age for the floodplain and calculate what the thickness of fines should be. So the nice thing is this kind of model comes up with this equilibrium geometry. And you can calculate the size distribution. Main input parameters, it's actually not much more complicated than the toy model. You have to have a grain size distribution now, but otherwise we just need the flow duration distribution, which is what we need for the toy model. You need channel geometry, we needed that for the toy model. We need a migration rate, we needed that before. Floodplain width, sediment supply, all of these things we needed in the model before. Okay? So stepping through it really quickly, we do the hydraulic calculations, range of flows. Once we have that, we do sediment transport, Wilcox and Crow, at each of those flows. Okay, that's capacity. Once we do that, we calculate the lateral exchange fluxes, so the river migrating into a high bank. This is a blunt, it's not a bank, but it illustrates the point. So we'll calculate, we'll bring material into the channel and then take it out of the channel at our specified rates. The rate going out is specified by the bar, but the rate coming in is a function of how much sediment is stored in the floodplain. We'll do an overbank deposition calculation as a function of the flow on the floodplain at all bins. We can do sand and mud if we want to. We'll do a bed change rate, and then if the bed is going down, then that means we have to essentially move material from our substrate back into our floodplain and channel. And if the channel is going the other way, we have to move material out the other way. Okay? And now, let's see, Artie's going to start running. What do the results look like? If we have no migration, And we put the dam in. This is 100 years of sediment starvation, so we're not simulating the dam removal here, just the creation of the dam. The river runs out of sediment really fast.